Hi everyone. Today we'll talk about vertical asymptotes and how we can find them using infinite limits. To understand the connection between vertical asymptotes and infinite limits, I have a quick exercise for us. We must draw a function with a vertical asymptote at x equal to 3 and then answer two questions. If you would like to try this exercise on your own first, don't forget that you can download these notes using the link in the video description. I start by drawing the vertical asymptote. There are various ways in which I could draw a function with a vertical asymptote at x equal to 3. I can draw it this way. 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 Let me choose one of those ways. What is the limit of this function as x approaches 3 from the left? As the inputs get closer to 3, the outputs grow without bound. They tend toward infinity. What is the limit of this function as x approaches 3 from the right? As inputs get closer to 3 from the right, the outputs tend toward negative infinity. This suggests that a function has a vertical asymptote at some x if the left-hand limit is infinity or negative infinity there, or the right-hand limit is negative infinity or infinity there. This is exactly how mathematicians define vertical asymptotes. The line x equal to a is a vertical asymptote if the left-hand limit is infinity or negative infinity, or the right-hand limit is infinity or negative infinity. If one of the one-sided limits is infinity or negative infinity, you know you have a vertical asymptote. Let's see if we can apply this definition to find vertical asymptotes of a few functions. If you would like to try this problem on your own first, this is a good time to stop the video. We are given the function x plus 1 divided by x minus 2. We must find its vertical asymptotes. In other words, we must find places where the one-sided limit, either from the left or from the right, is infinity or negative infinity. What are good candidates? I believe that x equal to 2 is a good candidate, because as the inputs get closer and closer to 2, the denominator gets closer and closer to 0, making the whole fraction bigger and bigger. So the first thing I do is I check the limit of this function, x plus 1 divided by x minus 2, as x goes to 2, and I need to choose from the right or from the left. I will choose it from the right. I need to check only one of those. Now, as x's get closer to 2 from the right, the numerator gets closer and closer to 3. The denominator gets closer and closer to 0. However, the inputs I'm using are always slightly bigger than 2, which means that the denominator is always slightly bigger than 0. So the denominator gets closer to 0 from the right. This tells me that this limit is infinity. In the numerator, I have a positive number. In the denominator, I get a positive number. So I get positive numbers as a result. What's more, the denominator gets closer to 0, making the whole value bigger and bigger. This means that this function has a vertical asymptote at x equal to 2. There's no need for me to check the left-hand limit anymore, because the definition says that only one of them needs to be infinity or negative infinity. I don't need to check both. As long as one of them is infinity or negative infinity, I already know that I have a vertical asymptote. Let's take a look at the second function. There are two possible candidates that I see. There are two x's for which the denominator is 0. It is x equal to 1 and x equal to negative 1. Let's check one-sided limits there. I start with negative 1. I take the limit of x minus 1 divided by x squared minus 1 as x goes to negative 1. I will this time choose negative 1 from the left. So I will compute the left-hand limit because previously I did the right-hand limit. When the inputs get closer and closer to negative 1, the numerator gets closer and closer to negative 2. In the denominator, I get closer and closer to 0. However, I'm using x's slightly less than -1. Let's choose one such x, for example, -1.1. When I plug it in to x squared, the negative goes away because a negative number squared is positive. So what is 1.1 squared? Well, that is definitely slightly bigger than 1. So when I subtract 1.1 squared and I subtract from it 1, I get a number close to 0 but positive. So in the denominator, I get numbers that are close to 0 but positive. I get a negative number divided by a positive number that gives me a negative number. Because the denominator gets closer and closer to 0, the whole fraction gets closer and closer to infinity. So I get negative infinity as my answer. Because I got infinity or negative infinity while computing the one-sided limit, I can conclude that there is a vertical asymptote at x equal to -1. What about at x equal to 1? Let me compute the limit of this expression as x goes to 1. Now I get to choose from the left or from the right. Instead of choosing, I realize that I can compute a general limit here. Because this expression is of the form 0 divided by 0 if I was going to plug in 1, which allows me to apply algebraic manipulations to compute this limit. Note that in the denominator, I can factor x squared minus 1. If I do so and I compute a general limit, I get the limit as x goes to 1 of x minus 1 divided by x minus 1 x plus 1. I cancel x minus 1 in the numerator and in the denominator, and I get the limit as x goes to 1 of 1 over x plus 1. Plugging in 1 gives me 1/2. This tells me that the general limit at 1 is 1/2. This means that the left-hand limit is 1/2 and the right-hand limit is also 1/2. So neither the left-hand limit nor the right-hand limit are infinity or negative infinity. So I can say that there is no vertical asymptote here at x equal to 1. Let's see if we can apply this reasoning to one more problem. If you would like to try it on your own first, again stop the video now. We are given a piecewise defined function. We must find its vertical asymptotes. I first look for candidates where possibly I have a one-sided limit being infinity or negative infinity. I look at the first formula and I realize that there is one x, which makes the denominator 0. That is x equal to 1. However, this formula is only used for x's less than 0, which means I will actually never plug in numbers close to 1 to this formula. So x equal to 1 is not really a candidate for a vertical asymptote. The top formula does not provide us any vertical asymptotes. In the second formula, in the denominator, I have 4 possible x's that make the denominator 0. 2, 1, -1, and -2. However, the bottom formula is used for x's bigger equal to 0, which means there are only 2 really candidates for vertical asymptotes, x equal to 1 and x equal to 2. Let's compute those limits. I'll take the limit of this function as x goes to 1 and as x goes to 2. Let's do it first as x goes to 1. I realized that I have the x minus 1 in the numerator and x minus 1 in the denominator. So these two things would cancel if I was going to compute the general limit. So I realized that instead of computing the left-hand limit or the right-hand limit here, I can compute the general limit. And I get the limit as x goes to 1 of x minus 1 divided by x minus 2, x minus 1, x plus 1, x plus 2. I can divide out x minus 1 at the top and at the bottom. And now as x's get closer and closer to 1, I get this number gets closer and closer to -1. This number gets closer and closer to 2. This number gets closer and closer to 3. So this limit is 1 divided by -6. So the general limit of this function as x goes to 1 is 1 divided by -6, which means that one-sided limits there are not infinity or negative infinity. So I can already say that there is no vertical asymptote at x equal to 1. What about at x equal to 2? I compute the limit of this function as x goes to 2. Now I will compute the limit from the left or from the right because I believe 2 is a good candidate for a vertical asymptote. Let's do it maybe from the right. And I get the limit as x goes to 2 from the right of x minus 1 divided by x minus 2, x minus 1, x plus 1, x plus 2. The numerator, x minus 1, as x's get closer and closer to 2, gets closer and closer to 1. X minus 1, as x gets closer and closer to 2, gets closer to 1. X plus 1 gets closer and closer to 3. X plus 2 gets closer and closer to 4. X minus 2 gets closer and closer to 0. However, we are using x's that are slightly bigger than 2. So this is getting closer and closer to 0 from the right side. So I have in the denominator 12 times numbers that get closer and closer to 0 from the right. So altogether, these numbers get closer and closer to 0 from the right. That gives me infinity. 1 divided by numbers bigger that get smaller and smaller closer to 0 gives me infinity. Because the right-hand limit was infinity, I can conclude that there is a vertical asymptote at x equal to 2.